This is a several part video where I'm going to go through and talk about how to calculate the pH of acid-base reactions. I'm going to start with a strong acid, strong base reaction, and then I'll get into a weak acid, weak base, and a few others after that. And I'll also take you through a particle representation. You could call this titration pH calculations if you want. So what I'm going to start with here, this is going to represent a 1 liter container, the sheet of paper, and I'm going to put 4 moles of HCl in. Now, right now we're assuming no volume change when I place those in. We'll see here in a moment how volume is a factor. But when I place those HCl molecules in, of course, because it's a strong acid, those fully ionize. And if I wanted to calculate the pH at this point, I would have my 4 moles of H plus in that 1 liter container. So I would do the negative log of that in order to do the calculation. Now I'll do those calculations here with some real numbers here in a moment, taking you through how that works. If I add in 1 sodium hydroxide, now what we end up with is the stoichiometry first. So we're going to represent any kind of a reaction. Well, if we wrote that reaction, we would write as a product NaCl plus HOH, but we know that the NaCl stays ionized when I place that into the solution. So I'm going to go ahead and I'm going to ionize that. And now the sodium, I'm going to sit down here beside the chlorine, although they're not connected, they're going to stay ionized. But this is going to bind up one of those H's to make a water molecule. So now all of a sudden I've got 3 moles per liter, or a 3 molar solution. Negative log, and I've got the pH. As I add in another one, stoichiometry first. You're going to hear that off and on through this video. Again, I'm going to set the Na here, and then we're going to show how it removes one of those H's. And now we've got 2 moles of H plus ions in the liter container. Put in another, and now we've only got 1 mole of H plus ion excess in the container. Put in another, now we reach the equivalence point. And for a strong acid, strong base titration, the pH at the equivalence point is going to be 7, because all we have here is water and sodium chloride. And sodium chloride is a negligible salt in terms of its pH, 7. And you got water, so because of that we get a pH of 7. Now if I go ahead and add 1 more sodium hydroxide in, now I've got 1 mole of hydroxide ion present in this liter container. So I've got a 1 molar hydroxide ion concentration, so I could negative log that to get the pOH and subtract that from 14 to get the pH. Now that's what it looks like kind of on a particle view representation. Now we're going to run through several steps here of a titration and do some calculations, and I'll go through these rather quickly, so if you don't get them you can always back up and kind of work through them again. But I want to know the pH of each of these upon the addition of no sodium hydroxide, 3.125, 6 milliliters, 6.25, 6.50, and 7 milliliters of sodium hydroxide. So I'm going to go through and do some pH calculations in order to find that. So the first thing, I have no sodium hydroxide. So if I want to calculate that pH, I have a 0.5 molar hydrochloric acid solution. So all I'm going to do is negative log 0.5, because it's a strong acid, it fully ionizes, so the H plus concentration is 0.5 molar, and I get a pH there of 0.301. Now, what happens when I add in 3.125 milliliters of 0.8 molar sodium hydroxide to my 10 milliliters of 0.500 molar hydrochloric acid? Well, the first thing I've got to do is the stoichiometry. I've got to do the reaction first. HCl plus NaOH, making NaCl plus HOH, and I'm going to go ahead and find my moles of each of these. So I've got 0.01 liters, or 10 milliliters, times 0.5 molar is 0.005 moles of HCl. Now that's going to be a constant through this problem, and Now we're adding in 0.8 molar times 0.003125 liters, and I get 0.0025 moles of NaOH. Now, that's half the amount of NaOH that I need to reach the equivalence point. Now, that's going to be a real significant value when we start doing our titrations with a weak acid and a strong base, but for now, really doesn't mean a whole lot. We're just going to do the calculations. So my limiting reactant, sodium hydroxide, show that it is limiting, and there it is. Show that we also react the same amount of HCl, and again, when I subtract that, 0.0025 from 0.005, I get 0.0025 moles of excess. Now, a moment ago, with the Legos, I said we'll assume no volume change, but here, now we've got a new total volume. We've got a volume here of 10 milliliters and 3.125, so 0.013125, or 13.125 milliliters. And I can get the molarity for that. 0.0025 divided by 0.01325, 13125. And I get a molarity here of 0.190 molar. And in order to calculate the pH, I'm going to do negative log of that value. And I get a pH of 0.72. 720. Alright, so now what happens when we add 6 milliliters? Well, my numbers here for the HCl are going to look similar. I've still got 0.005 moles of HCl, but I've added a different amount of sodium hydroxide. It's still 0.8 molar, but I've added 6 milliliters. So 0.8 molar times 0.006 liters gives me 0.0048 moles of sodium hydroxide. And again, with a 1-to-1 ratio, still not quite enough to reach the equivalence point. So it's still my limiting reactant. I'll show that it's limiting. Leaves me with 0.0002 moles of excess. And then again, the additive volume. I now have 16 milliliters, or 0.016 liters. So 2 times 10 to the negative fourth divided by 0.016 liters gives me a molarity of 0.0125 molar. And now to calculate the pH. Negative log, because it is a strong acid, that is the H plus concentration. And I get a pH here of 1.90. Actually 1.903. Alright, so now what happens when I add the 6.25? Well, at 6.25, the numbers change up just a little bit. So now when I get to 6.25, I've still got HCl at 0.005 moles plus NaOH. And now 0.8 times 0.00625 gives me also 0.005 moles. So at this point, I have no excess H plus or excess hydroxide. All I have is NaCl and HOH. And therefore, since this is a neutral salt and water, the pH at that point is going to be 7. Now what happens when I pass the equivalence point just a little bit? So I'm going to use this same problem that I had here. I'm going to mark that out now. And now 0.8 times 0.0065 gives me 0.0052 moles of NaOH. Now the limiting reactant switches. I've crossed over that equivalence point. So minus 0.005, showing there that the HCl is limiting now, minus 0.005, and I get really similar numbers to what I saw a moment ago, 0.002 moles, with one exception. The new volume here is now 16.5, 0.0165 liters, so 0.0002 divided by 0.0165 liters, and I've got my molarity of my OH, my hydroxide ion concentration, and negative log of that value gives me a POH of 1.916. 14 minus that answer gives me, try that again, 14 minus that answer leaves me with a pH of 12.084. So at this point we're at 12.084. I'll go ahead real quick and do the calculations for 7 milliliters added. So I get 0.008 times try that again, 0.8 times 0.007 liters gives me 0.0056. So I'm just going to use the same problem here, 0.0056. Again, I'm going to use up all of the HCl. I'm going to use up equal amount, leaving me with 0.006 moles in a total volume of 17 milliliters, 0.017 liters. And now I'm ready to calculate that molarity. 0.006 divide by 0.017, negative log of that value, 1.45, 14 minus that to get the pH, and I got 12.548. So if I were to plot this out, you can see that, I've added, a considerable amount of base to that point with not a whole lot of pH change, 0.3 to 1.9. On the other hand, I go just a little bit past that equivalence point, and now all of a sudden we're up to 12. And that's why, if we were to plot this out, we would get a pH curve that has a really steep vertical jump, which is why for a strong acid, strong base titration, we can use a lot of different indicators. Here we would have an endpoint relatively close to an equivalence point. Remember, endpoint is when the indicator changes. Equivalence point is the stoichiometry point. But we could use an indicator really that changes anywhere from about 4 up until about 10. Any of those indicators would work out fine for hitting relatively close to an endpoint near the equivalence point for that titration.